Hey physics kids, Campbell here. Today we're going to do some work and talk about changes in electric potential energy. So first we should review work. Remember work? Do some of you do work? Some of you don't do work, do you? Well, if you go back to AP Physics 1, remember work was if you apply a force, you can move an object and that changes the energy of the object. The work energy theorem says that work is equal to a change in energy. Today we're going to focus on changes in electric potential energy, but there are a lot of similarities to gravitational potential energy. So we're just going to start with a little review there. Now I have a ball here, right? And if I raise it some height, I increase its gravitational potential energy. If we draw a free body diagram of the ball, right, there's a force that I'm exerting to lift the ball up. And remember, when force is in the direction of displacement, that's positive work. But there's another force down on this ball, the gravitational force, right? This ball has mass, and so the gravitational force is in the opposite direction of displacement, and so it's doing negative work. So when I do positive work, I lift the ball, my force is in the direction of motion, and I increase the gravitational potential energy of the ball. While I am doing positive work, the gravitational force is doing negative work. So anytime the gravitational force is doing negative work, the gravitational potential energy of the ball increases. We can actually relate this to electric potential energy as well. If we bring a positive charge, so I have two positive charges here, and I want to get them closer together, right? They don't want to go that way, right? They're exerting forces of repulsion on each other. And so I'm going to have to do some work and apply an external force to move them close together. Kind of like this monkey here, right? The monkey has to, in order to get that positive charge closer to the other charge, has to do some work. It has to apply a force in the direction of motion, and it does positive work. This increases the electric potential energy of the system. When he lets go though, right, then the charge goes away. He's not applying a force then. The electric force is doing all of the work. It's positive and it is decreasing the energy. So what? Let's get into more detail here. All right, let's take a look at two like charges being brought together. So here is a source charge, and I'm going to take a little positive charge here and I'm going to move it towards that source charge. If we look at the forces involved, right, I have to apply an external force to move that charge because it doesn't want to go that way. And of course there's an electric force, that force of repulsion, trying to push it away, which is in the direction of the electric field. Now I am doing positive work because my force is in the direction of the displacement. And anytime the external force does positive work, it's increasing the potential energy. At the same time, the electric field, or that electric force, is doing negative work. So anytime the work done by the external force is positive, that means the work done by the electric field, or the electric force, is negative, and that will result in an increase in the electric potential energy. Now, what if it was a negative charge instead of a positive charge? Well, then no external force is required, right? You might have been wondering that last slide, why can't the external force and the electric force be in the same direction? Well, I mean, I guess it could be, but I don't need to apply a force, right? If I put this negative charge here around this positive charge, it's going to go that way when I let it go. So in this case, the electric force is doing positive work, which decreases the potential energy. So anytime the electric force does positive work, it results in a decrease in the electric potential energy. Now, there is one thing I want to point out here. Notice that the electric force is in the opposite direction of the electric field. But don't get all worried about that. Remember that electric field direction is set by what charge is present. So if I have a big positive charge present, the electric field is away from it. But if I put a negative charge there, then it's going to feel an attractive force. So the force is going to be in the opposite direction of the field. Not a big thing to worry about, but it'll be something that will mess you up. So I always think about, instead of thinking exactly what is the direction of the electric field, I think what is the direction that charge is going to want to move. If the charge moves in a direction that it wants to go, that means the electric force, the electric field, is doing positive work and its potential energy is going to decrease. Just kind of like if we drop a ball, right? It goes in the direction it wants to, it loses potential energy. But if a charge moves in a direction it doesn't want to go, the way it wouldn't naturally go, so we have to apply a force, then we are doing positive work, the electric field is doing negative work, and that will increase the potential energy, just like if I lifted a ball. Now, we're going to get into in the next video how these equations came about, but the electric potential energy equation is KQQ over R. Notice it's very similar to the electric force equation, which is KQQ over R squared, and that can lead to some problems. But the unit of energy, right, is the joule. Oops, J for joule. And it's an interaction, right? I need two charges present in order for there to be an electric potential energy, just like I need two charges present in order for there to be a force, KQQ over R squared. But sometimes it's better to talk about one charge. Remember with forces, we talked about fields, and the electric field is a modification of space around a charge that if we put another charge in there, it would feel a force. Well, we have that same sort of idea for energy. It's called electric potential, and it's symbolized by a capital V, not a little v, that's velocity, capital V. So it is the potential for energy. So just by putting this charge in space, there is the potential around it for energy. All I got to do is bring another charge in its presence, and then now I have electric potential energy. It's kind of like height with the gravitational potential energy, right? I can put a ball at any height, right? And I now have gravitational potential energy, but that potential exists even if the ball's not there. So electric potential, kind of like electric field or like a gravitational field, it's the potential for energy. Now, we usually talk about it in terms of differences in potential, and we then usually talk about it in terms of voltage, because in fact, the unit of electric potential is the volt. So when you talk about batteries, right, you talk about, I don't know, 1.5 volt batteries. Well, batteries have the potential to give you energy. You just got to put them in a circuit, and then you got energy. So potential, if we take our electric potential energy equation, we plug it in here, it's the potential energy per unit charge. So when we do that, notice that Q disappears and we're left with this equation, which kind of looks similar to that equation, which kind of looks similar to the electric field equation, except there's not an R squared on the bottom. I know, sorry. All right, now energy is a scalar, which is wonderful, right? Then I don't have to break things into X and Y components. Life is good. But then you have to remember to use the sign of the charge when you do your potential or electric potential energy calculations. So if we look at a negative charge, and in fact, if we graphed it, right, would be an inverse graph. It would look like that, a nice little steep curve there. And it's negative because it's a negative charge. Now, anytime we're around a negative charge, we call these areas of low potential. It doesn't mean that it has low potential or that you have low potential. It just means that it is an area around a negative charge. It could be a really high number, but we still call it an area of low potential. For a positive charge, right, we have our positive KQ over R, and there we have our positive graph of potential, an inverse graph. And we call areas around positive charges areas of high potential. Now, it could be just like 1 volt, but as long as it's a positive charge, it's an area of high potential. So make sure you know that terminology. Low potential just means negative charge. High potential means positive charge. All right, equipotential lines. In physics, we like to visualize stuff, especially with electrostatics, because it's like, wow, what's going on here? And we already talked about electric field lines, right? Electric field lines are these red lines in this picture here on the screen. And they show you the direction a positive charge would move. What an equipotential line is, or also called an equipotential surface or an isoline, sorry, lots of words, same thing, is an area in which the potential all along that line is the same. So anywhere, and those are the green dashed lines here, anywhere along these green dashed lines, the potential, that KQ over R, is the same value. Now, a couple interesting things about equipotential lines and field lines. an equipotential line is always perpendicular to an electric field line. So when we draw our field lines, you can notice here, like especially here, this one in the center is straight vertical because the lines are horizontal in the very center. So perpendicular, equipotential lines are always perpendicular to electric field lines. And so if you get a map of one, you can use it to draw the other. Electric field lines always point towards lower values of potential, right? They point towards areas of low potential because remember, electric field lines point from positive to negative. So they always point towards negative, which is an area of low potential. Very, very importantly, no work occurs when a charge moves along an equipotential line, right? Work equals a change in potential energy, which means there needs to be a change in potential. So if there's no change in potential, no work is done. Remember that. Write it down and star it. So if I take a charge and I move it anywhere along here, I'm moving it, right? But I'm not changing the electric potential energy, so there's no work being done. So this diagram here, which I want you to draw for your equipotential lines, are for equal but opposite charges. And in fact, if you can imagine, right, if we do KQ over R plus KQ over R, but this one's negative and that one's positive, here in the center, we're going to get a value of 0 volts. All right, so that is a 0 point. And in fact, we could look at this like a topographical map. They like to, because equipotential, and I'm going to talk more about this, is very similar to this idea of gravitational potential. A topographical map, which if you've ever hiked, right, a topographical map looks like this. And you see these lines, and those are lines of the same height, right? Gravitational potential energy is about height. And when the lines are closer together, that means, like here, it's steeper. And it's the same thing for equipotential lines. When equipotential lines are closer together, like here in the middle, that means the potential is changing faster. Now, this picture here, up here, is actually that 3D map for this set of charges, the opposite charges. Notice how the negative charges must be my negative charge down here, and that's my positive charge. The negative charge is negative, so it's down. And the positive charge is positive, so it's up. And here, right, that's my 0 voltage line, equal but opposite charges. Let's take a look at a couple other different maps because you're going to have to be able to identify these. This is the equipotential map for same sign charges. Now, these are both negative charges. So if you think about it, I've got these two negative bowls going down. And it's not like there's a 0 point. So notice there's no line in the middle like there was in the last one because there's no 0 in between the two charges, right? The potential, if we add, right, every time we add potential, right, we're adding numbers together in the middle. So anytime in here, we're adding stuff together. So it's never a 0. There's never a 0, and that's why you don't see a 0 here on the equipotential map. And in fact, as you get farther away, that's when the potential goes down, when I have same sign charges. In fact, I kind of like to think of these as when I have the same sign charges, as this is kind of like a mask. Like here are my eyes. Whoops, there's my face. It's like a mask. All right, what about parallel plates? Remember, parallel plates have uniform electric fields. Of course, we also have some bowing on the edges here, right? If we want to be technically correct. And equipotential lines must hit those lines perpendicular, so we get nice straight lines. Of course, out here, they're going to kind of, well, that one goes straight. They'll kind of bow, right? Because they got to hit it perpendicular. But because there's a constant field between parallel plates, the electric potential actually increases linearly as you move from the plate of low potential to the plate of high potential. So notice I go from 0 volts, the difference, total difference between the plates here, right, is 10 volts. But as I move across, in the middle I'm going to be 5, and then halfway between the 5 and 0 is 2.5. So notice a very linear increase. And in fact, I can use this equation that voltage change, that potential difference, is equal to the electric field times the change in distance from the plate.